So Professor Martin Guest will continue his lecture on this gamma classes and TT star structures and U structures.
Okay, thank you very much. Good, so here's the equation that we were considering. Recall the differential equation from last time. So this differential equation is the quantum differential equation transformed. So it's basically the quantum differential equation with a new variable, right? So my usual notation for the quantum differential equation has a q for the variable, but this variable is well, it's basically the cube root of q. So I'm just talking about the 3 by 3 case, which means we're talking about the quantum cohomology of CP2, P2. So we make this transformation and we get a nice equation. It's nice because the leading coefficient is semi-simple, right? It has distinct, it's diagonalizable with distinct eigenvalues. And well, that's a matrix equation, but of course it's related to the vector equation. So by x, I mean the vector x0, x1, x2. And if you convert it, you get a scalar equation for the scalar component. So let's just take the scalar equation x0. So this is basically the scalar quantum differential equation for CP2. Okay, so well, it's a general principle that let me just say, in general. Suppose we take a basis of solutions, I mean of the scalar equation, x0. So I'll call it x0, 0, 0, 1, x0, 2, right? So this scalar equation for x0, the three-dimensional solution space, I take a basis. So we obtain, of course, capital X, and then we obtain a chi. So a solution, a matrix solution chi of the first equation. Yes, okay, and then, well, so then logically my notation, I extend my notation by saying this is x0, x1, x2. Okay, so this is a column vector. So I can do that. So, well, the strategy, so what am I trying to do? Well, I want to produce the gamma class, and I want to produce it as the connection matrix of this differential equation. So the strategy to find the connection matrix, which I call dk, or well, dk, and gamma class, is to find, first of all, gamma class of CP2, is to find, is to look for a nice solution of the matrix equation, and it's going to be constructed from the scalar equation. So we choose a suitable solution. Well, I choose a suitable x0 equals g. Well, x0 is zeta. And then I'm going to choose, after I've done that, I automatically get a basis by defining x01, x02, like this. So these are still solutions of the equation. Why? Well, what is omega? Omega is the cube root of unity. Why? Well, because the equation that I started with, it only contains zeta to the power 3, right? So when you multiply by omega, it doesn't change the equation. And it's easy to see they're independent. So that's going to be the strategy. Well, that's the starting point. And then relate this chi to the two things, to the special kind of solutions we had last time, which is 0 and infinity. So zeta equals 0 is a pole of order 2. And there we have Stokes phenomenon, Stokes sectors. And then at infinity, we have regular singularity, so we just have one kind of Frobenius type solution. And then we find d. So dk will be the difference between these two things, which if I find relate explicitly chi to these things, and then I will find my explicit d. So that is the strategy. So we need some differential equation theory to do this. So let me state this as a theorem. So 3 ways to solve the differential equation, the scalar equation. I mean, this is a classical differential equations theory to solve this equation. Well, the first way we've already seen, Frobenius method. So I will call it a Giventhal Frobenius type solution. Type. Which in this, so of course it's not exactly the Giventhal solution because I transform the equation, but the analogous equation, solution, I'm going to call it G for Giventhal. So the Giventhal type solution is 3 to the minus 3d. And then we have some gamma functions. And then we have zeta, 3d, 3x plus d. So remember, x is, as usual, the generator of H2. Integer class. And so it is the same kind of thing that we had with the Giventhal solution of the quantum differential equation. So I think I wrote that properly. Well, this is cohomology valued, so I can write it as G0 times 1 plus G1 times x plus G2 times squared. And this G0, G1, G2 will be a basis of this type, right? It will be a different basis, but it's a basis of this type. So we can certainly do that. The other way, well, there are two ways, but they are both giving convergent integral formula. I mean, the integral is a convergent integral on a sector. Well, I'm going to take a particular sector of the zeta plane, so pi over 2. I mean, this looks funny, but I'm just choosing it to fit my notation. So it's minus pi over 2 to pi over 2 shifted by pi. So this is a convergent series, of course. So this is actually convergent everywhere. And then there's a convergent integral. Well, there are two kinds, so let me write them both. So the first one, okay, integrals. And the first one, well, I'll put it here. So 2a. This is what's called a Millian-Barnes type integral. And formula is, so this is going to be little g. So I said I'm going to look for a suitable g. And here it is. Well, here's one possibility. So one possibility is the contour integral of gamma cubed 3 to the minus 3 t e to the minus 3 pi I t and zeta to the minus 3 t dt. T is my kind of generic variable. So when I talk about ODE theory, I usually use z as the complex variable, but in the contour integral there are two variables, so I use t. And the zeta is our usual zeta. Zeta is our zeta. These are maybe not very important, but the important thing is gamma and zeta to the minus 3t. So you can check that this satisfies the equation. And you can check that it's convergent. The integral exists on this particular sector. Then we have the so-called oscillating integral, and this I will write the formula, so 2 pi I divided by 3. Okay, well, e to the pi I is minus 1 here, but I'll still write e to the pi I. And this is a double integral. Well, many people know this, so it's maybe a familiar type of integral, Landau-Ginzburg type. I mean, this appears in mirror symmetry, right? And x1, x2 are, well, they're the integration variable. It's a real integral. So this oscillating integral also exists. And in fact, it's absolutely equal to the previous integral. So the reason I call it g zeta is because it is g zeta. It's equal to the previous g zeta. And so remark that 2a is equal to 2b by, well, 2a leads to 2b by transforming it like this, by substituting the definition of the gamma function. So gamma z is e to the minus t to the z minus 1 dt. So you substitute it into the first integral, and then you put, well, let me see, but there are 3 gamma factors, so I want to do it 3 times. So, I mean, namely, the substitution, well, each gamma factor I will consider separately. So each gamma is an integral like this, but now let me change the notation and call it tau instead of t. Instead of t, right? So tau j. So instead of z, I have 1/3 minus t minus 1 d tau j. J will be 1, 2, or 3, 0, 1, or 2. So there are 3 gamma factors, and I introduce 3 new variables. And then I define x1, x2. Then put and then finally, so why do I only have 2 variables? Well, because we integrate out. Integrate with respect to tau 0. So if you do that, you convert 2a to 2b. They're equivalent. So I guess this is a fairly standard thing. I mean, I would never think of doing this, but it's apparently a well-known transformation. So they're both the same thing, but each version has its own advantages. And we're going to use that. So these are the 3 ways. So there are 2 ways, 2 integrals, 2a and 2b, and then there's a series integral. Yes, well, okay, I will continue on this point. Okay, so now, so this will define chi, right? Because I define my little g. So now we want to consider the special solution which we got from the Stokes phenomenon at z equals 0. So concerning this, the following, I'll call it a theorem. This chi 0, which is the holomorphic solution of the Stokes sector, k equals 1. So the first Stokes sector, this is equal to chi times some constant. And the constant is actually rather simple. Constant matrix, but it's not the identity, but it's almost the identity. So minus 3, well, of course, I'm using some very particular notation, so all the constants are very messy, but that's omega squared. And what is c? C is another constant. It's actually the square root of 3 over 4 pi squared I. So this is so what is the proof of this? Well, proof. It's a quiz, so I should give proofs, right? At least one proof. Actually, I'm not going to give the proof. I just said it. But I'll tell you the idea of the proof. So the point is that we, how was this function chi 0, how was it defined? Well, it was defined in terms of the formal solution. So it has the property that on this particular Stokes sector, which I defined last time, it's asymptotic to the formal solution. So we need to know something about the asymptotics of our chi. And that we can do so you can compute the asymptotics of, G, first of all, as it goes to 0, in the Stokes sector, using the second one is good for that, 2b. Well, I suppose you can probably do it from 2a. But anyway, from 2b we can use the Laplace method to get the asymptotics. And we find that, in fact, it looks like this. So it's asymptotic to the same constant to 1 over c, e to the 1 over zeta. Well, it's sort of what you would expect as zeta goes to 0. So that means we also get the asymptotics of the 2 other solutions. So this is omega, right? Omega divided by zeta, and omega squared. So this is good because remember the formal solution. So recall that the formal solution which I had last time, well, there's some kind of series which is not so important. I'll just put a box there. And then the important part was the exponential of some matrix, and that matrix, diagonal matrix, was exactly the expected. I mean, it was exactly what I get over here. So this is good, right? So this almost means they're equal. Well, might be some constant, but in fact that's not true. They're not equal. And the reason they're not equal is because the asymptotics doesn't quite work. So the Stokes sector, what was my Stokes sector? My Stokes sector was, so this is defined by, I mean it's characterized by being asymptotic to the formal solution on the first Stokes sector, and this Stokes sector was minus 2 pi over 3, 2 pi over 3. Okay, so that's the characterization of chi of 1. And the G, well, we know that the G has this asymptotics on on this, where is it? This sector here, on this sector. So you can, and so then you deduce the asymptotics of the second solution and the third solution, and they're almost the same, but they're not quite the same. The sectors do not match, so you are in trouble, right? You cannot immediately conclude that they're equal. So we almost have this, but we don't. So in fact. Well, in fact, we get this. So, in fact, okay, let me say this very informally. So, actually, the second and the third are okay, but not the first one. I mean, because this sector is not. You see, zeta is not, so that means that zeta is minus 3 over 2 to minus pi over 2. So this is completely wrong for this. So it doesn't, it's not good, but not G. So we have to know, we have to unfortunately compute the asymptotics. We have to do some more work to compute the actual asymptotics on the Stokes sector. And it turns out that you can do this. It's a little tricky, but there's a kind of recursion formula satisfied by G, which is that. So I'm on the universal cover here. So even though omega cubed is 1, that does not mean zeta. It means going around by 2 pi. Now, so it's easy to check that, but by using this formula, you can extend your asymptotics a little bit, and well, you get to the modification that we need. So the modification. So you see, G2 and G3, sorry, G1 and G2 are okay, but the first one needs some modification. So that comes from that. And that's what people always do when you read classical textbooks and they calculate the asymptotics of a Bessel function or Airy function or something. They always use some trick like this. I think if you don't have that, you just can't do it. I mean, it's just not easy to compute asymptotics. But when you have something like this, you can do it. So we get the first theorem. And why do we have this recursion? Well, it's because, this property that the equation only contains zeta to the power 3. It's because of that. The equation has some. Well, it's not only because of that. I mean, it's because this equation has such a nice sort of cyclic symmetry. That's the reason. So it seems like all the famous equations have some nice symmetry which can be exploited like this. Okay, then theorem 2 is about the other one. Theorem 2. So chi infinity is equal to. So I want to compare it to chi, and again there will be some constant matrix, but what is that constant matrix? Well, it is a product of two matrices, which I call gamma and V. And so I won't write it explicitly, but gamma contains gamma function coefficients. Well, I mean, the Taylor expansion, gamma 1 plus z, that Taylor expansion contains some numbers like zeta 1, the Riemann zeta function. So it contains coefficient constants like that, and V is, it's a generalized van der Monte matrix, so I call it V. So I won't write down what it is, but anyway, the proof of this is by using the other integral. So using using 2a. Oh, I got rid of it. So the Mellin-Barnes integral, you use the residue theorem to to calculate the integral. Compute G by the residue theorem. Because the gamma function has poles, right? So gamma 1/3 minus t. Well, we have the cube of that, has poles at which points? Well, 1/3 plus d. So you can make a picture like this. So we have poles 1/3 plus d. And so you integrate over some, well, I said minus infinity to plus infinity, so it goes like that. That's why I have minus 2 pi I. That's why it's a minus. And you can apply Cauchy's the residue theorem. See, the rest of the integrand is holomorphic, so it doesn't affect the poles really. And well, you can do that. So compare the answer. Compare the answer with what? Well, with chi infinity, right? But chi infinity is essentially the Frobenius solution. So it's the Giventhal solution. The Giventhal type solution actually just times a constant diagonal matrix. So if you compute this and compare it with that, you find this matrix B. So it's a bit complicated because of course it contains the residues of this function, right? So gamma coefficients will appear. But we can do that. So then we get the connection matrix. So the conclusion is that, so I have to copy my notes, conclusion. So that's the end of theorem 1 and theorem 2. So the conclusion is that we get an explicit formula for D1. Right, because it's just the difference, it's the D1 is the difference between, remember the definition of D1 last time, chi infinity is chi 0, 1 times D1. So that's what it is, so we get that. And then knowing this, so what I explained about the so-called principal asymptotic class of Galkin, Golechev, Piratoni, in the first lecture, we get that explicitly from this. So the principal asymptotic. So the thing which I explained kind of roughly in the first lecture, that is actually part of the connection matrix. Essentially, it is the connection matrix. Or it comes from the connection matrix. So good, so we can do this. However, we do not yet quite see the gamma class. I mean, certainly we see gamma functions, but what is the, why should this be the gamma class? I mean, cohomology class. Well, okay, so that's the next point. Where does the cohomology class come from? Probably better to use the middle, right? So I'll use the middle. Well, you have to, so the answer is here, but you have to reorganize it a little bit. Yeah, so any questions so far? I'm just applying classical ODE theory without really thinking about the meaning or interpretation. Just ODE theory. And we have a connection matrix which we can fortunately calculate because we have this very symmetrical differential equation. Okay, so the cohomological expressions. Where does that come from? Well, you do a sort of magic trick. It's a trick. So we have the formula. Okay, let me divide by, because I want to use the residue thing. Maybe I forgot this before. So I want to use this because using the residue theorem. So our expression our integral, the million bounds integral is this. Let's call, so these are holomorphic functions, f and z. These will be holomorphic at the poles. Interesting point is the poles of this. So let's have a look at this. Well, I put the minus there because of the contour going the other way, right? So contour is going clockwise. Okay, so by the residue theorem, this is equal to equal to the sum of the residues. And this is the coefficient. Well, it's the coefficient of 1 over 1/3 plus d plus. It's the coefficient of v to the minus 1. So I'm going to introduce v as this expression. So 1 over that expression for the residue for the Laurent expansion, and the coefficient of 1 over that. If I convert the integral, it's that, right? T is v. You have to watch carefully or you will miss the magic trick. Well, so the first point is that I replaced the sum over the residues, which are infinitely many, by sum over functions. I just now have one pole here. But still, that's a true equation. And then I think about my gamma part. So let's rewrite this in a convenient way. Let's rewrite this as so I'm just rewriting the thing in the box. So gamma minus v cubed so I didn't do anything, right? This is just putting something in the top, something in the bottom. So this is the same as, by the property of the gamma function, and well, this one here is minus v minus 1, v minus d, all cubed, which is minus 1 cubed, well, that's minus v to the minus 3, gamma 1 minus v cubed, and then I take out all the minuses here, so minus 1, well, that's also, well, that's, anyway, it's minus 1 to the 3d times something which starts to look familiar from last time. It looks like the given tile solution, so this is cubed. Right, so this box is equal to this. Sorry?
Your box gamma don't have cube.
Oh yes, thank you. Thank you. This is, well, they're all cubed, right? Yeah, this is cubed and this is cubed. Yeah, thank you. So this is equal to, well, I wanted the coefficient of v to the minus 1. But I already, you see, in the denominator, I already now have a v to the minus 3. So actually, it is the same as the sum. Well, it's summed, of course. Yes, I forgot to say sum here. So d is not changed, right? D is going from 0 to infinity. 1 to 0. So this is coefficient of the v squared of the rest, right? So in minus 1, well, let's gather all the minus 1s together. So I'll put it back in the gamma form now. So I just put this one back like this. 3 to the minus. Oh, it's still, okay, so minus 3d minus 1 times zeta to the And yes, now I do another magic trick. Now I put V to be X in the cohomology. Well, V was originally a real number, right, or a complex number, but now I put it into this ring. Which is okay because I'm dealing with a Taylor series here, so it's no problem. So I can do that. So the conclusion is that I get sum of coefficient of V squared in sorry, so no, I got rid of V. V is X. So in terms of X, well, I just have the same thing, right? It's it's gamma 1 minus X now. This becomes the gamma class, right? Times, well, the rest of it, you see, it's just the given Tal solution. It's G of X. Well, zeta X, I mean. G depends on both X and zeta, but it's just polynomial in X. Times of this, and then minuses basically cancel out, right? But then I still have something. I still have these 3 is a bit annoying, but anyway, this is actually not a very important thing. But the other things are important, because they all have a good meaning. So this is the cohomological expression. And so, of course, I can write this formally. Well, not formally, I mean, it's really true. I can write this as this nice cohomological formula. And this is the formula that we usually see in the gamma class literature. Well, it's times this funny. Well, let me just put that in parentheses. It's just basically log 3, right? It's just some constant which is not so important. And so taking the coefficient of x squared means evaluating on the fundamental class, because we're talking about CP2. So it's this. So we have a nice cohomological meaning. So what did we do here? Well, basically, in terms of matrices, let me write a matrix formula. So this should have something to do with D1, right? And it does. So if you consider the chi solution, this is chi, right? And then, well, I put here 1 over 2 pi I minus 2 pi. This is equal to the given Tal type solution times something. Well, let me just say star, star, star. So, of course, this is the connection matrix, right? So this is essentially chi infinity, essentially. And this is not quite D1. I suppose in my notation, this is what? Yeah. So remember the definition of D1 was like this. Actually, I'm writing it the other way around now. So this is chi 0. No, this is chi. But yes, I take away the B1 matrix, and just have left here, yeah, this matrix is gamma times V without the B1, yes. I just kind of forgot the B1. Right, so you see chi is almost chi1, but there's a B1 matrix which has been lost now because this calculation tells me this. And then we have the rest. But the first, the formula which I just discussed is this times this, right? And what about the other part of the connection? So this should be the part of the connection matrix. Well, the point is that G, if you put an omega inverse in front of the zeta in your equation, you see it doesn't really make a lot of difference. Yes?
Why does it gamma be the inverse? Because originally you had it on the other side.
Oh yeah, you're right. So chi 0 is yes, D1. So what was my notation for?
Chi infinity equals to chi
Yeah.
b. B is minus 2 pi gamma.
So this should be inverse here.
And those should be the inverse.
Be inverse. Maybe. Oh, okay. Thank you. Yeah, so this doesn't make a whole lot of difference. We basically just get an extra e to the 2 pi I x. Why is that? Well, we have zeta to the power minus 3. No, we have in the given tau solution we have zeta to the minus. Yeah, we have. This is basically what we are looking at, right? If you put a omega inverse in front of the zeta, well, omega is e to the 2 pi I over 3. The d will actually go away because it's 3d, and you're just left with x, I claim, 2 pi I x. And then similarly for this one, four pi. So that's what it is. And of course, the cohomological interpretation of these things are, so basically this thing gets interpreted as well, in the notation which I used last time, the first column is the gamma class, and I could just say it's the Chern class of all 0. And then the second column is the gamma class times the Chern character of 1, and then the gamma class times the Chern character of 2. So this is, of course, CP2 gamma class, which I defined last time. So that's kind of nice. So we got the rest of the matrix for free, basically. And that's the formula. So this is basically the Dubrovin conjecture for CP2. I mean, it's the ingredient of the Dubrovin conjecture for CP2. Well, I didn't say anything about the Stokes matrix, but the connection matrix is the gamma class times the Chern characters of the exceptional sequence O1, O0, O1, O2. Yes, now what are the difficulties here? So this is, of course, I mean, I said last time there are some difficulties because you're choosing a lot of different things. You're choosing notation, choosing a reduction of the differential equation, choosing Stokes sectors, all that kind of thing. But there are more difficulties. So the difficulties, well, I would say that there are, okay, difficulties. Yes, so difficulties of not so much in the formula, there's nothing wrong with the formula, but of the interpretation. Of this formula. So, well, yeah, let me just say, this is, I hope this doesn't sound impolite, but this is basically ignored by Galkin, College of Iritani, and it's treated in some detail by the other three authors, Cotti, Dubrovin, Guzzetti. So the difficulties are, first of all, there are two difficulties. Yeah, so in terms of my calculation, the B1 matrix has been forgotten, right? And this represents an ambiguity in the braid group action. So this is, I will call this braid ambiguity. And secondly, well, I don't know quite what to call this, but let me just say, in terms of the calculation, in terms of this picture with this matrix, then there are some constants floating around here. So the constants, and this is, you might call this the Levelt ambiguity. So it's not exactly the ambiguity in the Levelt normal form of chi infinity, but it's related to that. So there are these two kinds of difficulties which are ignored by GGI and are treated carefully by CDG. Well, you know, the point is, actually, the problem is that you see this, the result here is, I would say, it's too beautiful. So they are geometers, right? So they want to get a beautiful answer. And the answer, the discussion of CDG is, yeah, well, I hope they don't mind me to say this, too ugly. They are analysts. Well, they are differential equations people. So geometers, we always want to get a nice answer. Differential equations people, they don't care how nice it looks, right? They're happy to get it. So, and this is the problem. And well, you know, so one of the points of my giving these talks is that I would like to find some intermediate way, right? There should be something slightly better than CDG, but not quite as beautiful as GGI. But I don't have an answer, unfortunately, yet. So it's not entirely satisfactory situation, but this is the problem. So this is what I mean by difficulties. There's, of course, nothing wrong with the theorem or the calculation, but there's still, I feel, a nicer way, intermediate way to write the answer. But I don't know what it is. Yes, what was I going to say? Anyway, not entirely satisfactory, so still perhaps something to think about. You can't avoid some ugliness because, you know, the braid group is quite difficult to deal with. You can maybe hope to deal with the constants, so that's something I will talk about next. Yeah, so actually for the rest of the time, I would like to talk about what my actual talk is supposed to be about, the real structure. Right? So on the abstract it says TT star equations and the real structure. So what do the TT star equations have to do with this? Okay, so final part, the real structure. Well, this has to do with the so-called TT star equations, and I should say what is the TT star structure. In the case of CPN, so of course it has a completely general definition, but for CPN, in particular CP2, what is a topological, anti-topological fusion structure? Well, it is a family of metrics. actually inner products, real inner products, on the cohomology space, the real cohomology space. Although perhaps better to say so this is a subspace of a complex. Well, we're always using this, right? So when we're talking about differential equations, we always want to use the complex. Obviously, we have meromorphic equations, Stokes structure, and so on. But it's perhaps better to say here a constant matrix conjugating this, where C is the complex matrix, which looks like this. So the diagonal 1, antidiagonal is I. So some sort of rotation of that within the complex. So it's not quite the usual real cohomology, but it's rotated. It is a Q family of inner products which satisfy the Tt star equations. And what are the Tt star equations? Well, in this case, it's a kind of Toda equation. So a Toda type partial differential equation for some, well, so the inner product, I'm going to, so it's just a real inner product, and I can, actually, it can be diagonalized in this case. So I'm going to take the matrix of the inner product to be the diagonal matrix with some positive edges, and these Wi's are real valued functions, right? So Wi is actually a function of Q. In fact, it's a function of the absolute value of Q. So it's a Toda type equation for these Wi's. So I won't say any more about but so you can find the explanation of this in Dubrovin's paper. So the definition was Chakotay, Vafa, Rand. Right? So paper published in 1991, and then Dubrovin, 1993. Communication in mathematical physics, maybe. He showed that these Tt star equations, in general, not just for CPN, but the Tt star equations are equivalent to the flatness of a connection. So Dubrovin showed that this is an integral system. It is a zero curvature equation for a certain connection. So I will not write the definition of alpha, but it contains these functions, Wi. If you know the Toda equations, well, it's basically the usual flat connection. And furthermore, there's another way to describe it, is isomonodromy condition. So it's integrable in two senses, because isomonodromy deformations come up in the Penlever equations very famously. And Tt star is of this type. So let me just say for certain alpha hat. Well, so you have these equations, and so you might think, well, this doesn't really have much to do with quantum cohomology. But actually, it's part of the structure, so we should not ignore it, really. It's part of the structure. And the authors I mentioned, GGI and CDG, they don't use this, although the early papers of Iritani did use this point of view. And in fact, the physics paper I mentioned yesterday, paper by Zaslov, which explains this Tt star point of view. So we have this, and we'll try to use it. Well, the reason I can talk about this is because I know how to solve these equations in the CPN case. So my joint work with Professor Itz and Professor Lin is that we solved this equation. So there exists a unique solution of these equations, which I didn't write down, but the Toda equations, such that the asymptotics have a certain form, which in this particular case for quantum cohomology is actually this. As Q goes to 0. Q is now the quantum usual quantum variable. And then W1, so I won't write the others, partly because in the n equals 2 case, there's only really W0, because we actually always have the condition that Wi plus Wn minus I equals 0. So in the 3 by 3 case, the W1 is automatically 0. We just have W0 and W2, but W2 is minus W0. So I won't write any more about that. So when I say solution, I mean solution on the entire complex plane. So for the entire C star. So actually the problem is it's not obvious that you can solve the TT star equation. So in the case of CP1, so Iritani knew this because Chikote-Laffer also knew it, and it was known since the 1970s. But for the higher CPNs, well, we didn't know this, what the solutions. Actually, solving the PDE is apparently easy. You know, this kind of PDE, the Toda equation, in this case, it's something which PDE people can do before they have breakfast. It's a very easy thing, right? But of course, you have to do a lot more stuff because you have to relate it to the Stokes structure and the connection matrix and so on. So it's not only a matter of solving the PDE. So in the non-abelian Hart correspondence, which this is a special case of, you know, basically PDE theory tells you can solve the PDE, but it doesn't tell you so much else. Anyway, continuing this same theorem, I should say that because we have this flat connection, there's this solution corresponds to an alpha, right? So there's a certain alpha, and here is where you see the relation to the quantum cohomology, because it turns out that this alpha is actually, as q goes to 0, well, as q. It's not really asymptotic, it's just in a neighborhood of q equals 0. Well, it is asymptotic, yes, I should say. So it's asymptotic to the quantum differential equation, which I wrote yesterday like this. Well, before I put lambda equals 1. So this is the usual, well, it's the transpose because just the way I'm writing connections. So it's the transpose of the matrix in the quantum differential equation. And it turns out that this alpha is closely, is approximately the quantum Dubrovin connection at 0. That's part of our theorem, actually. So what does this mean regarding the connection matrix? So what does this say about D1 and the gamma class? So how does this affect the gamma class? Okay, well, so I calculated D1 precisely, right? And in the papers by Cote, Dubrovin, and Guzzetti, they do it in the general case, CPN, also the Grassmannian. But what does this mean? You see, the problem is that, so my equation is not actually the original quantum differential equation because I changed the variable and I also did a gauge transformation, right? So I'm not really dealing with, so I should say, this is essentially the quantum differential equation with that. It's essentially that, but not exactly. So how did I convert? Well, if you remember, I did a little gauge transformation and that contained some constant matrix. And what we really want to do is go back to the quantum differential equation. So this is not exactly, this is kind of the heart of the matter if you're thinking about differential equations. But if you think about the interpretation, it's not quite the answer. So what does it say about, so that's the end of the theorem. What does the theorem say about D1? Well, so I don't have time to explain this carefully, but it's a fact that the actual connection matrix of the quantum differential equation of CP2 is, well, first of all, you have to multiply by that constant matrix, which I had yesterday, so I don't explain this again. But yesterday I had this constant matrix, and then it turns out that there's another thing. So exponential of, well, plus or minus, actually. I'll just write the plus case. A Nilpotent matrix like this. Now, I can't really explain this. So this, I mean, I can explain that because it comes from the Gauss transformation I did yesterday. But actually, the Gauss transformation yesterday was slightly oversimplified. And I really need another matrix in the quantum cohomology case. So let me just briefly say that this is related to alpha approximating. The omega does not mean the cube root of unity. Omega means this one, right? So, yeah, I'm sorry, that's the Dubrovin connection. So, and this actually comes from something called the Kurosawa factorization. And yesterday I didn't mention this, but actually in the quantum cohomology case, it's unfortunately not quite the most obvious thing. You have to put in some extra matrix, and this is the matrix you have to put in. Anyway, the interpretation of this is another fact. The matrix, so yeah, these matrices, I mean the new things which go beyond D1. So these matrices represent the second ambiguity, the one which I call 2. Okay, so the first ambiguity was the bright ambiguity, and this second one, well, it has to be, it's related to these constants. So this is the ambiguity of the constants. So what I claim is that given by, this actually depends on the solution of the TT star equation. I didn't explain this, but it's actually, you don't quite see it from the leading term of the asymptotics. You actually see it from the next term. So there is not in fact a unique solution if you just specify the leading term, but there is a unique solution if you specify the second term, and that has to do with this A. So this A is related to or corresponds to having a solution on the entire range Q. You see, actually, if you just specify the leading term, you can get local solutions easily like that. But to get a global solution on the entire complex plane, you need to choose this. You need a more careful choice of asymptotics. Yes. Okay. So this kind of suggests another problem. So for the last few minutes, let me take a slightly different viewpoint. Well, I'm still talking about the real structure.
One thing I'm a little confused about is that, so these matrices, they appear in the solutions of the TT star equation.
Mm-hmm.
But then you said that these are related to the ambiguity and constants of the solution of the just quantum.
Right.
So could you elaborate on that?
Yes. What I probably should have said is that the omega So this omega, I mean, actually, you know, if you're just interested in the quantum product, then you're mainly interested in the scalar quantum difference equation, right? Because it's the relations in the cohomology ring. Or you're not so much interested in the choice of basis. So I made a choice of basis, and actually you need a bit more flexibility. So what I should do is I should put in some constants. So C0, and instead of 1, I put C1, and here I put Cn. And actually the A, which so this is a choice of. It's a special value, a special choice of C0. Well, in the 3x3 case, there's only 3 of them, right? So it has to do with that. Well, of course, you want to have the product. So we want to have C0, C1, C2 equals, well, 1, let's say. And then we still get the quantum cohomology ring, as usual. But there's a choice of basis, which we need a good asymptotic basis. That's what people say. Okay. Right, so it's slightly different change-up. So you say, well, okay, we have one particular solution of the TT star Toda type equations, which corresponds to the quantum cohomology of CP2. Well, what about other solutions? Why don't you consider other solutions? And in fact, this was exactly the point of view of Chakotay and Weffer. So they really wanted to solve the TT star. I mean, they believe that the solutions of the TT star equations, not only in the CPN case, but more generally, should have some physical meaning. So let me just say a few words about that. So a change of viewpoint. Let's consider general solutions. Of the TT star equations. Well, of course, I'm only going to consider the Toda type. Because that's the only case where we know how to solve them. So Toda type. The general solution really means general solution. It means all the solutions. So there's a theorem about this. So this is in our papers, which were written here at 10 years ago, more than 10 years ago. And actually it's also proved by Mochizuki from the Hodge theory point of view. And in general, it's a conjecture of Chakotay-Weffer, which we only verified in this one case, that the solution of TT star, well, let's call it TT star Toda, actually corresponds 1-to-1 to some asymptotic data. So now I'm talking about CPN, such that, well, these m's are real numbers, and they satisfy this symmetry condition, and they are constrained like this. So that's actually a compact set. It's a polytope. Which I studied in some detail with Nanko Ho, who's here. It should have some interesting meaning, this polytope. Anyway, that's another story. But this correspondence goes through the asymptotics like this. Okay, so of course the special values of m correspond to the quantum cohomology. So let's just talk about the 3x3 case. So these are all the global solutions. And in the 3x3 case, this is very simple because this diagonal matrix is just a line. These conditions mean that it's the values between -1 and 1/2. Actually, this was known by Chakotay-Weffer. So if you look at their original paper, you'll find this 3x3 case. Although they didn't I think they didn't quite have the solution of the TD star equation in that case. They had it in the 2 by 2 case. So how does this look? Well, the point is that we have, okay, so I should say what is quantum cohomology. So here is the M0 line. So I draw a picture with -1 and a half. So it's this interval, right? So the polytope is just a one-dimensional polytope. And Chakotay-Vafer's point of view was that the physical solutions, and not all the solutions, but the physical solutions are the ones which have integer Stokes matrices. I mean, they're all integers. So, on the first day I said that the Stokes matrices are basically constructed from the binomial coefficients, which are integers. So they're an example of this. So actually, in this case, it is the point -1, M0 equals -1, which corresponds to P2, to CP2. So it's just one point of this interval. And well, actually, so Chakotay-Vafer wanted to use this as a basis to classify field theories. In fact, the title of their paper is Classification of Supersymmetric Field Theories. So that's what it's about. What are the other integer cases? Well, there are not so many. Of course, 0 is kind of a trivial case. M equals 0, well, the equations become quite trivial, right? So Stokes matrices are the identity. But there are some other cases which are kind of interesting. So actually so this condition in the 3 by 3 case, it only allows these particular numbers. So the endpoints and 0, but also I want to say something about -1/4, because this is actually an important case. 0, 1/2, -1/4, -1/2. And this -1/4, they already, no, right, 1/2, right. So -1/2 actually is another kind of physical interesting, -1/4 is an interesting, so this one actually corresponds to the so-called A3 singularity. I mean, it's the field theory, the Landau-Ginzburg model corresponding to A3. So then puts a different point of view, right? So no, we would like to perhaps interpret all the solutions, at least all the physical solutions, in some nice way. Just as we can interpret the quantum cohomology solutions corresponding to M0 equals -1. And in particular, it means that we should have a nice connection matrix in these cases. So what connection matrix do we get? Okay, so this is my final point. Maybe one thing I can make a remark, because it's related to some of the previous lectures by Konstantin and also by Sander-san today. So these equations, see, we changed. I guess I should say. Well, I will say that next. But the point before I get to the 3 by 3 example, let me just remark that these Toda equations correspond. So the ODE corresponding, the zeta ODE corresponding to M0 to M. So for each choice of parameters, you get a different zeta equation. So it won't be exactly this. It will be something different. And the scalar equation will be different. Well, actually, this looks like, I will just say looks like, the equivariant case. For complex Primitive space, so for CPN. So let me try to make that clearer in the 3 by 3 case, because I want to go back to that case next. Yeah, so the situation is that we have this whole family of sort of quantum cohomology. Well, they're not really quantum cohomology because, of course, the Landau-Ginzburg A3 model, this is not quantum cohomology, but they are field theories. And we have some nice candidates for the, well, we have calculated the connection matrix, okay, and we sort of more or less solved the second ambiguity. So the second ambiguity I claim is provided by the solution of the TD star equation, which is a PDE, so it's not quite obvious from the algebraic point of view. The first ambiguity, the braid ambiguity, well, that's always going to remain. So I have nothing more to say about that. But let me just finish with a few comments about this A3 case. Yeah, actually, I would like to say that the connection matrix given by the TT star equations is an intermediate one between the very beautiful one and the very ugly one. But I can't honestly say that because it still looks ugly to me. But in this case, I can say something. So let me tell you about this. Well, you know, it probably looks ugly because I still made some bad choice. Or maybe I just made a mistake in my calculation. Anyway, the A3 case. So the analog of the quantum differential equation. I mean, it's no longer a quantum cohomology thing, but it's a Q equation. I'm just talking about 3 by 3. Although the same thing applies to general N. Yeah, so the usual Q and the usual Y and, well, 1 over lambda, if you like, would be this for this case, right? So this is M0. That's why you have these numbers like a quarter and a half there. So it's a fact that in this case, yeah, so if you write down the corresponding zeta equation and scalar equation, that will look like the equivariant quantum cohomology look like. Okay, so the second fact, the fact is that the connection matrix of this Q equation is, there isn't any nilpotent matrix, so it's just the diagonal matrix, so the Gates transformation which I did yesterday is absolutely correct. That's what we do, there's nothing more to say. But the A, which is given by the TT star equations, is the square root of gamma 3/4 gamma quarter to the minus 1. And the D in this case is a diagonal matrix, so it doesn't, I didn't tell you actually, no, I should say that what did I call it? That we had we had V gamma, right? Or maybe it was gamma inverse, V inverse. And the V is an elementary thing, but the gamma is the interesting one. So the gamma, in this case, is actually, okay, then I need more space. So it's sort of the gamma class in this case, although there isn't really a gamma class in this case because we don't have any nilpotent matrices floating about. So gamma is actually diagonal matrix. And I just want to write what it is. Okay, so these three are the diagonal entries, and then I multiply it by this matrix for these particular A's, which are from T star, T star. So if you just look at the original D, well, you have some gamma functions, and that's what it is. But if you take account of the TT star structure, the real structure, then you get something modified. And actually, if I wrote this correctly, then the punchline is that this does not contain any gamma functions anymore. So we get, so using, of course there are gamma functions there, but if you use the identity, if you use the gamma function, you see we have a quarter and 3/4, right? If you use that, the gammas basically disappear. In the modified character matrix. So I don't know whether that's significant, but at least it's beautiful, right? The gamma functions have disappeared. Well, they're converted to sine elementary functions, right? So whether or not something like that happens in the quantum cohomology case, I'm not sure. But it should be slightly more beautiful than the general situation where we did not consider the TT star structure.
Very similar to the spatialization parameter of the quantum variable. I mean, because in all the type 1 and type 3, there's extreme contraction. And type 3 with genus at least 1. So that could be developed to canonical transition. In canonical transition, we know there are just finite sum of the formula tells us we just substitute the quantum variable to be 1 under the limit. But if you just look at the original differential equation, the hypergeometric equation, it's quite complicated. And actually, when you calculate it, it looks like everything depends on the other variable terribly. But then you just do the calculation and substitute every gamma formula like what you have.
Good.
And also the derivative of it, you have this psi function, over psi function, this sum of 1 to 1, 1 over 2 to 1 over m. But then you just compute it then all of them cancel out. You still get
good.
So all the gamma disappear.
Good. Okay, so I stop here.
Questions?
So you said there are five, I guess, five solutions with integrals for.
Oh, yeah.
So what about the other?
Yes. What about the others? Well, this is the endpoints are quantum cohomology. So actually, this is the weighted predictive. I'm not quite sure what is a good notation, but it is a weighted predictive line. Okay. So then orbifold quantum cohomology. This is just trivial. And this one, well, I'm not really sure. It comes from some singularity, like A3, I guess. Yeah, it's somehow the interior ones are, have this character. Well, not all of them, but, well. Yeah, anyway, this one is orbifold quantum cohomology.
But also, like, for example, I mean, in this gamma formula that you have for one, was it negative 1/4? Negative 1/2? This last one? The H3 case.
Yeah, this is for minus 1/4.
Right.
Yes.
So in this case, it looks a little bit like orbifold quantum cohomology as well because of.
Yes.
There are also gammas. Yeah, there are also diagonal radius and twisted sectors where essentially you have gamma of fractional.
Okay. Yeah, so actually the fractions are probably not very significant because I remember this notation I'm using is q d by d q. So if you change the power of q, you can sort of normalize this. You can normalize them away actually. But in the case of this endpoint, it's meaningful to keep them. Yeah.
Other questions? If not, thanks, speaker.
Thank you.